Hello, water activity. Every food scientist, technologist, and engineer must know. My basic degree was in chemical engineering. I had no idea on food science or technology until I started my MSc thesis on drying of pineapple. As soon as I entered into food science, technology, or engineering in 1984, the first term I learned was the water activity. Still, I am learning the water activity. Today, I am going to explain basic understanding of water activity. This is my first video on the water activity, and I am planning to make more videos on the water activity. First, we need to understand partial pressure of gas in a closed chamber. It contains air, that is mainly oxygen, nitrogen, carbon dioxide, and water vapor. Each gas provides a pressure in the chamber, that is partial pressure. Higher water vapor in the chamber can create higher water vapor pressure. Now we could see what happens when we place a bunch of grapes in the airtight closed jar. Water in the grapes is marked as red, and water in the air space, that is gaseous phase, is marked as pink. Water movement dynamics will start due to the difference in the energy state of water. That is, water will escape from the grapes as well as return on the grapes. Water molecules will try to reach energy state equilibrium when chemical potential of water in the grapes and the gaseous phase reaches at equilibrium. The chemical potential is the driving force in this process. The water vapor molecule in the vapor space creates the partial pressure of water vapor. As I mentioned earlier, more water molecules in the vapor space will create more partial pressure of water. This water vapor pressure at equilibrium condition and water vapor, if we keep pure water instead of grapes, define the water activity. It is important to mention here that it should be at constant temperature. Thus, water activity is the ratio of these two water vapor pressure. At the end of this video, I will explain more on the theoretical thermodynamic basis of water activity. Now we can bring it into simple experimental basis. We can place a saturated salt solution at the bottom of the desiccator at constant temperature. Saturated salt solution will create a specific relative humidity. For example, if we place a saturated salt solution of sodium chloride, then it will create a relative humidity of 0.75 inside the desiccator. A layer of salt crystals at the bottom will ensure the solution remains at saturated condition during the experimental period. A food sample in a dish can be placed inside the desiccator to equilibrate a relative humidity of 0.75. Now we can write the water activity equation. At equilibrium, water activity is the ratio of the vapor pressure of water in food and vapor pressure of pure water at constant temperature. In addition, water activity can be considered as the equilibrium relative humidity of the air in the desiccator. The experiment will provide the equilibrium moisture content of food at the water activity of 0.75. Water activity varies from 0 to 1. Water activity indicates the energy state of water that is strongly bound These are monolayer water. And then weakly bound water, these are multilayer water, and free water is weakly bound water. Free water is in a high energy state. Free water could be used by chemical reactions and microbial growth. Strongly bound water contains low energy state and most inert. Thus, chemical reactions and microorganisms are unable to use this water. Multilayer adsorbed water contains medium energy state, thus medium reactive. However, free water contains high energy state, thus very reactive and available for the chemical reactions and microorganisms. Is water content and water activity same? Consider same food, for example, fresh and dry apricots, that is same compositions without water. Water content of fresh apricot is 80% and water activity is 0.93, while dried apricot contains 22% of water with water activity of 0.62. Therefore, water activity and water content are not the same, but there is a relationship, that is decreasing water content decrease the water activity and vice versa. In the next video, I'll explain the difference of water activity and moisture content in more details. Why water activity, not water content? In 1950s, William James Scott, an Australian biologist, clearly identified active water correlated well with the microbial growth in foods rather total amount of water. As I mentioned earlier, water activity indicates the state of water, that is its activity. Therefore, generalized rules or limits could be developed for the determination of microbial stability of foods using water activity. For example, no microbial growth can be observed below water activity of 0.60. The details of the generic rules will be presented in one of the next videos. Water activity concept originates from the energy state thermodynamics of foods, while water content or moisture content is composition of a food. Water activity originates from the chemical potential, fugacity, and thermodynamic equilibrium. The chemical potential can be written as, therefore here we need to understand few things. One is chemical potential and fugacity to address non-ideality and thermodynamic equilibrium. The chemical potential is a driving force in the transfer of a material from one phase to another and provide a basic criterion for phase equilibrium. The free energy, that is chemical potential of component I in a gas phase at pressure Pi, can be written as, this equation is valid when gas phase behave ideally, which is only very low pressure. Lewis proposed a new function f called fugacity to valid at all pressure. Fugacity is a measure of the escaping tendency of a vapor. It is then applicable to real system, whether mixed or pure, ideal or real. The equation can be written as. We can now consider food water vapor interaction. At a constant temperature, all components and water in foods are in thermodynamic equilibrium with each other in both the absorbed and vapor phase. In this case, we can write the equilibrium conditions in terms of chemical potential. Solving these equations, we can define water activity as AW equal to PW divided by PW naught at constant temperature. Therefore, water activity is ratio of vapor pressure of water in food and vapor pressure of pure water and constant temperature. In addition, water activity is equal to the equilibrium relative humidity of the surrounding air. If we add solutes or solids, water activity will decrease, or if we add water, then water activity will increase. The question now, how much? The increase or decrease will depend on the amount as well as types of solutes or solids, that is, for example, molecular weight and interactions with the solids and solids with water. Thank you for watching my first video on water activity.